Okay, so welcome back to another video. Here we have a little, I like to call this like a rational exponential function. So if we're given that f of x is equal 1 divided by 2 to the power x plus 1 divided by 3 to the power x, so all the way so on and so forth, it ends at 1 divided by 4,000 to the power x. Then we want to find what f of 2 plus f of 3 plus f of 4 and then so on. It's infinite, in other words. So I think it's also interesting to see that the procedure behind this is basically you want to, as we see, we want to evaluate what f of 2 plus f of 3. So it's always good to check, like if you plug in those values for x and plug it back to your original function and then see what kind of behavior you can pick up from there. Now, of course, doing things at one at a time, we can probably see what the bigger picture is. Obviously, you're just simply plugging 2 and each of these x replacements. And then if you do this for specifically at the nth variable, you're basically just basically the same thing as saying f to the x, so just replace n with n for all this. So you might be thinking, what can we do from here? Well, it's also worth noting that taking all those sums together, there's actually a pretty neat geometric series that's going to be involved with this entire process. So I think I pretty much just gave most of it away, but so let's actually go through this entire thing together. Let's start with f of 2 since that's our first. So let's just take a look at something. So f of 2, so of course that's going to give us 1 divided by 2 square. Add this with 1 divided by 3 square. Add this with 1 divided by 4 square. You get the gist. It just ends to 4,000 square. All right. So let's, for example, let's say we try 3. So 1 divided by 2, 3, then plus 1 divided by 3, 3. Add this with 1 divided by 4, 3. I'm just skipping this saying the powers, but you know where I'm coming from with this. So 4,000 to the power 3. Okay, let's try one more number, and then I'll skip to all the way to the nth term. So that's supposed to be a 2 to the power 4 over here. So 2 to the power 4, add this with 3 to the power 4, add this with 4 to the power 4, then all the way up to 1 divided by 4,000 to the power 4. All right, so if we just keep going all the way down, then for some nth number, f of n is going to equal, basically, it's just the same function, but just plug this back for n instead. So 2 to the power n plus, so 3 to the power n, add this with 1 divided by 4 to the power n. Then we just stop at 1 divided by 4,000 to the power n. And so now, of course, we want to evaluate what f of 2 plus f of 3 plus f of 4, f of 5, f of 6, all the way up to, it's all the way up to infinity. So we can actually create this little infinite sum. So let me call this this evaluation over here capital S, and we'll write this as an infinite sum, and we'll start this index at n is equal to 2 of f of n. Okay. So what I can do here is, since we wrote down everything, like after plugging in for each of the variables or for replacing for those values one at a time, we can actually do a little bit of grouping. So we're actually going to put all the bases together in a way, and then we'll follow each of these by ellipses. So for example, in this situation, I'll first put as 1 divided by 2 to the power 2, add this with 1 divided by 3 to the power 3. These are grouping everything with the same bases all the way up to the 2n. So let me actually now follow this with an ellipse. And we do this for the same thing again, but for the different base. So here we're going to be doing with 2 to the power, or hold on, that's supposed to be, wrote the wrong number. So that's 2 to the power 3. Then over here, this is going to be 3 square. Add this with 1 divided by 3 cube. Let me just move one more line down, follow with another ellipse. You see how the situation goes. We're actually grouping by these bases together. And so if we just go all the way to the end, well, really, we still have the 1 divided by 4,000 to the square. Add this with 1 divided by 4,000 cube, and then it's infinite. So this actually just continues on, so on and so forth. And then as we notice over here, is if you take a look closely, this is actually each of the bases that we follow, like before it reaches each of these ellipses. You can actually see that this actually forms, as I mentioned in the beginning, a geometric series. But be careful how you actually, put in the geometric series formula, because we actually have a different index. So it's not n is equal to 0 or n is equal to 1. So it actually follows with n is equal to 2. So for this situation, it's usually you have your ratio divided by 1 minus that ratio. But since we're starting at a different index, we're actually starting at n is equal to 2. So we have to evaluate this for the n equals 2 term. So in other words, if I put it this way, we have first what follows by 1 divided by 2 square divided by, then 1 subtract your common ratio. So that's where the because that's where the index starts over here. So we just keep going. So 1 divided by, or plus 1 divided by 3 square, then divided by 1 minus the common ratio, which is 1 over 3. This is actually okay to say because, you know, each of these ratios are strictly less than 1, so it's actually valid to use this. Then we do the same thing. So 1 divided by 4 squared, then divided by 1 minus the common ratio, 1 over 4. But just keep going on, so on and so forth. Then this actually goes to follow to 1 divided by 4,000 square, then divided by 1 minus 1 divided by 4,000. And so from here, let me actually group this a little bit differently for the multiplication, I mean. So you'll see that 1 over 2 square, so I have a 1 minus 1/2, so I'll just put that, you know, obviously that's going to be 1/2, and I'll put that 2 under the denominator. So here we get this new, you know, rewritten expression. This is going to come down to, you know, 1 divided by 2 square, then times 1/2. Then add this with 1 divided by, you know, 3 square times 1 over 3, so on and so forth. And then we see we get 1 divided by 4,000, 1 divided by 4,000, then multiply by, or square, and then multiply by 3,999 divided by 4,000. Okay, and so now we can do, what we can see here is that we actually have some of the numbers that cancel each other out. As you see that the 2's will cancel, so we're left with a 1 divided by 1 times 2. Add this over here, so the 3's will cancel, and we're left with a, actually that one's actually supposed to be a 2 since it's a 1 minus 1 over 3, so that's a 2 over here. So that will make sense to say we have 2 times 3. We see another pattern if you just keep following that pattern, so this will be 3 times 4. Go on all the way up to 1 divided by 3,999 times 4,000. Then as you can see from here that we can actually do a little bit of a partial fraction decomposition, write things well, each at a time, and we can have that this is 1 minus 1 over 2 for this term. Then add this over here, do the same thing, so it's 1 over 2, then subtract 1 over 3, add this with 1 over 3 minus 1 over 4, add this with 1 over 4 minus 1 over 5. Just keep going, and then all the way at the end, this is 1 divided by 3,999, and then what is it, minus 1 divided by 4,000. And as you see over here, we have some terms canceling out, so this is actually a telescoping series. So we have that the halves cancel, then the 1 over 3's and the 1 over 4's, 1 over 5's, keep going, so on and so forth, and then the 1 over 3,999 cancels, and so now we're just left with 1 minus 1 divided by 4,000, and so therefore this simple math, we can see that this is actually going to the sum of the functions f of 2 all the way up to infinity is going to equal 3,999 divided by 4,000, and just like that we are done. That was actually a pretty interesting procedure that we just went through. But it all relies on, you know, doing a little bit of grouping, and then eventually we get to using the, you know, geometric series to follow this answer just like so. So yeah, that's pretty cool if you ask me.